Good afternoon, everyone. We're going to go ahead and start into our second video of this unit. Still looking at the idea of stoichiometry, but now we're in section 2. So, our goal for this video, I want to be able to use my knowledge of stoichiometry to convert from one substance, from moles or grams of liters of one substance, to another using the balanced chemical equation. Some of you may have an idea of where this is, at least be on the started path. That's perfectly fine. If you're completely lost in the dark, don't worry, we're going to take some time. We're going to walk through a couple of examples. We're going to see if we can't get you ready to go. So let's go ahead and get started. Hopefully by this point you've already rated yourself. So let's get moving. Now, when I get ready to do any type of stoichiometry, it's going to involve that table that we've dealt with before. Now, if I'm only asked to go from moles of one substance to another to moles of another, that's actually going to be much easier. So let's take a look at the example. We're back to our same 2 moles of aluminum oxide decomposing into 4 moles of aluminum and 3 moles of O2 gas. Now, each time we use 2 moles of aluminum oxide, we're going to make 3 moles of O2. We understand this part. So this actually gives us our mole ratio that we're going to deal with. Now, remember I said that mole ratio, let me write it up here, was, I'm going to make it shorter and go MR equals moles you want over moles you have. So, in the case of what we're dealing with here, I can set up my mole ratio depending on what I actually need. These are the 2 options that I have based off of my chemical equation if I'm focused on aluminum oxide and oxygen. Well, let's take a look if we're actually going to use this. It says how many moles of O2 are produced when 3.34 moles of aluminum oxide decompose. Now, in the previous slide, we set up our possible mole ratios. Well, since we have our 3.34 moles of aluminum oxide, that means we also need aluminum oxide on the bottom, so we'll be able to cancel it out. So 3.34 moles aluminum oxide times our conversion factor, 3 moles, which I pulled from my equation, over 2 moles of aluminum oxide. Now, if this is all that we're looking for, from moles of one to moles of the other, we can actually go ahead and calculate this just as normal. 3.34 moles times 3 divided by 2, which is going to give us our final answer of 5.01 moles of oxygen. So when 3.34 moles of aluminum oxide are decomposed, we're going to form 5.01 moles of oxygen. You can check the math just to make sure I haven't done anything crazy, so you'll be able to understand and see what's going on. Now, if you know the amount of any chemical in the reaction, that means reactant or product, we can always find the information for all the other chemicals or all the other compounds in that formula. As long as I have the equation and I have some type of number to work from, in this case the 3.34 was my given, I can find out information about any of the other items in that equation. That means whether it's how the reactants are going to come together and how much will be formed, or how much of the products will be made, or how much of the products can be made from these types of different things. So let's take a look at another example. So here we have 3.84 moles of C2H2 that are burned. This is our ethine or our acetylene. How many moles of O2 are needed? So in this case, we're not going back and forth on both sides of the equation. We're actually looking on the same side. Well, taking a look, we have 3.84 moles C2H2. I'm going to set up my table. Now, since this is here is my given, that means my 2 moles, according to my equation, 2 moles C2H2. And on the top, we're trying to find out how much O2 is needed, so that's 5 moles of O2. Now, since it's only moles to moles, it's a one step. 3.84 times 5 divided by 2, I should come out with a final answer of 9.6 moles approximately. Okay? Now, a lot of these are set up so that you can go through on your own and sort of take your time and make sure that you understand what's happening. I'm going to go ahead and move to the next part. Similar type of setup. This one I want you to go about doing. How many moles of C2H2 are needed to produce 8.95 moles of water? Your final answer should come out to approximately 8.95. Now, some of you are probably going to look at this and say, okay, Mr. Baldwin, well, why are you giving us the answers if you want us to go about doing this? Well, in terms of stoichiometry, the big thing that people struggle with is the process, how to set it up to get the correct information. I have no doubt that you can find the correct information. I want to make sure that you can understand the process of how we got it, and then that you can use that information or that know-how, that knowledge, to be able to use and apply to other situations. That's the goal. Now, if you like, there's this last one here on the screen. Take your time, come back to it, pause, and work through it to make sure you understand what's going on. Now, each of these equations, or each of these problems, came from the same equation, same balanced equation. All we did is looked at the relationship between two different compounds within the same equation. Given a certain amount, how much of this one can I make? Now, the key of how we get good at this is always going to be practice, practice, practice. So if you look at your package, you notice that it's full of practice on these different types of problems. So you can get used to it and you can sort of understand what type of process you're going to be going through. Okay. Now, steps to solving stoichiometric problems. First, balance the equation. Notice number one is not to do any math or anything like that. It is to balance the equation from what you're given. Second, convert the given amount into moles. Third, set up mole ratio. Use the mole ratio to calculate moles of desired chemical, and then convert back into the final unit. There's a packet that you're going to have that will help out a lot with understanding how and what to do in terms of stoichiometry problems. My goal is that you will use that information, that packet, to give you sort of a stepping stone to move on to the rest of the practice. Now, we can use this same process, but now going instead from mass to mass. So before we did mole to mole, and it was just a one step. Now if we go mass to mass, there's another part that we have to go in. So we're going to jump to actually from one step. Now we're going to be dealing with 3 steps. Now in your head you may be saying, 3 steps, it sounds like a lot of work. It's actually not as bad as you would think. Now, the way that we know that we're looking at a mass or a 3-step problem says 6.50 grams of aluminum reacts with an excess of oxygen. Excess of oxygen just means there's a lot of oxygen there. You don't have to worry about calculating or running out. How many grams of aluminum oxide are formed? So going from grams to grams. Well, let's take a look at what we have. 6.50 grams of aluminum. How many grams of aluminum oxide? Well, the first of our 3 steps is we need a molar mass. We have to somehow convert from grams of aluminum to moles of aluminum. So we do that by our molar mass. Grams is here, so grams needs to go to the bottom so we can cancel it out. 26.98 we get directly from our periodic table. Now, the next step we said is our mole ratio. Again, mole ratio, MR, moles you want, over moles you have. So the moles we have in this case are aluminum. The moles we want are aluminum oxide. According to our balanced equation, whenever I put 4 moles of aluminum in, I get 2 moles of aluminum oxide. That works out fine. Now I get a chance to cancel out my moles. Last thing I need to do is convert to the final wanted unit, which is going to be grams of aluminum oxide. So it's another molar mass. So 1 mole at the bottom, molar mass of aluminum oxide at the top. Taking the time to calculate it, and a lot of people make little mistakes here, so you want to be careful with your molar masses. Now, note that here for the last step, in this first step, the number of moles is always going to be based out of 1. Because of the fact that we're trying to find the molar mass in each of those steps, It's always how many grams in 1 mole. The only time we change that is when we do our mole ratio, oops, which comes from our balanced equation, which is given to us here. Okay? So you want to make sure you have that very clear, very straightforward. Now, to figure out the last part, all we need to do is multiply what's on top, divide by what's on the bottom, and we come out with our final answer. If you have your calculator with you, take your time and go through and make sure that you understand how to do it. So that's 6.5 times 1 times 2 times 101.96, and then we're going to divide that after we've multiplied the bottom part, 26.98 times 4, and then once we get that value, we go ahead and divide out, and we come with our final answer of 12.3 grams of aluminum oxide. So when 6.5 grams of aluminum reacts with an excess of oxygen, meaning it completely reacts, none left, we're going to produce 12.3 grams of aluminum oxide. Okay? Now, this was a 3-step problem, but we still worked it out in the same way. There's some of you who will prefer to do 3 separate steps. Sorry, works just fine. You should still come out with about the same answer, okay? But you want to make sure that in the end, you write not only what the number was, but the unit and the compound. This is where the compound part becomes so crucial, because it tells me what exactly it was that I was focused on in that reaction or in that equation. Now, looking at another quick example. If 10.1 grams of iron are added to a solution of copper 2 sulfate, how many grams of solid copper would form? I have my balanced equation here in front of me. 2 moles of iron plus 3 moles of copper sulfate produce 1 mole of iron 3 sulfate and 3 moles of copper. Well, oops, let me go back. Just like we did before, 10.1 grams Fe. Need to convert from grams to moles, so that means grams Fe, moles Fe, 1 mole. And if I'm not mistaken, sorry, looking for my periodic table, I believe we're looking at 55.85. I want to verify this before I move on. For those who think I've memorized the periodic table, far from it. 55.85, okay, we're there. Alright. The next step is my mole ratio. I have how many iron, and the question is how many grams of solid copper are going to form. So I'm worried about this and this. Well, the moles I have, 2 moles Fe to produce 3 moles of Cu. Last step, I need to go from moles of copper into grams of copper. So 1 mole of Cu, 63.55 grams Cu. And again, multiplying what's above the line, dividing what's below, I'm going to come out with a final answer of approximately 17.2 grams of copper. Now, you can take your time and look back at this example and make sure you understand sort of what's going on with this process. The idea is going to remain the same. Okay? Now, the last section that we need to look at in terms of this part is volume to volume calculations. Now, just like we did with the number of molecules or atoms, it's going to be very, very similar, and you'll look at it and you'll say, okay, this part is going to be kind of easy. It says, how many liters of methane, CH4, at STP are required to completely react with 17.5 liters of oxygen? We have our balanced equation in front of us, so let's go ahead and get started. Well, 17.5 liters, and we know that at STP, 1 mole of any gas has a volume of 22.4 liters. So, 1 mole over 22.4 liters. Why do I know it's the 22.4 is at the bottom? Well, liters is here, so that means liters has to be at the bottom, so I can get rid of it. Now, mole ratio like we did before, According to my equation, 1 mole of CH4 to 2 moles of oxygen. Well, set it up. It's good to go. And last but not least, I need to go back to my desired unit, which is going to be liters. So 22.4 liters over 1 mole. Now, my hope is that you catch something, that the first and the last step are basically the same. Why is that going to happen? Well, again, understanding that relationship, 1 mole of any gas at STP, which it tells you it's at STP, is going to be 22.4. So basically, it just tells us that it's going to be half the volume of methane to go with the total volume of oxygen. Pretty straightforward, right? I know. Nothing too crazy so far. Now, what I want you to do is, I want you to take the time and I want you to rate yourself. Where are you at? Do you feel like if I was to give you any problem or a basic problem in stoichiometry, you could actually convert, whether it be moles to moles, moles to grams, liters to liters, or maybe grams to liters, or anything like that of any stoichiometry problem, sorry, that you'll be able to actually go through and do it. Maybe you feel like you're a little bit better as far as explaining how and what to do. Take the moment, rate yourself. We're going to actually go through this more in class tomorrow. Make sure that you're ready to go, and I'll see you then.